Hello, my name is George Samet, and as part of my research, I explored how one might use expected monetary value, or EMV, to manage technical debt. Technical debt is a metaphor used to describe not quite right software. It is continually discussed in terms of principal and interest. The principal is the cost of doing it right at the present time, and the interest is the overhead in excess of principal or the cost of doing it right in the future. It is an easy metaphor to understand, that it will be more difficult and expensive to change and maintain substandard software in the future than in the present. However, it is an exceedingly difficult metaphor to quantify, which confounds the decision-making process. When is it advisable to accept technical debt? When is it advisable to reduce or remove it? This paper aims to expose analytical tools capable of answering such questions. Since there's a real cost associated with technical debt, it is proper to discuss in financial terms. Furthermore, since it is considered a risk, it is proper to discuss it in terms of risk. Therefore, a risk-based financial model is the most appropriate mechanism for managing technical debt, and the model chosen here is a cost-based EMV approach. This slide shows the categories of technical debt with respect to their popularity in the current research. Since it is common to discuss multiple categories in a single paper, you'll note that the percentages exceed 100%. Initially, technical debt was deemed a code problem, but as may be seen here, it has since expanded. There are two additional categories worth exploring since they are relevant to the two new management categories proposed in this paper, as you will see in a few slides. Intentional technical debt is accepted and added to the code base as the result of a decision and is often part of a trade-off. Unintentional debt is a result of poor development practices or inept developers and tends to be caused by looming deadlines. It is often less visible than its counterpart. Similar to the previous slide, this slide shows the categories of tech debt management with respect to their popularity in the current research. Again, note that the total percentages exceeds 100%. Repayment deals with reducing or removing debt. It is frequently done unofficially. Identification is usually performed using static code analysis or manually, the latter adding a significant overhead. Measurement is usually accomplished through some mathematical model and has been shown to be ineffective if done at all. Monitoring deals with observing tech debt and its effects over time. It is rarely done. Prioritization deals with ordering debt and making decisions about removal. Communication refers to techniques to elicit discussion. Prevention assumes it is possible to avoid technical debt in the first place, and representation is often used as a visualization tool. It rarely occurs. This paper concentrates on tech debt measurement and prioritization, the former being requisite for the latter. Clearly, tech debt prioritization is under-researched. One additional categorization not seen in the literature relevant to this paper deals with how tech debt is handled. Reactive tech debt management is a decision that is made when the debt is unexpectedly encountered during the development. Proactive tech debt management deals with decisions made before the work commences. Both of these will be addressed later in this paper. We now turn to a discussion of economic analysis techniques relevant to the related research, as well as the position proposed in this paper. Economic analysis deals with decision-making based on financial comparisons of alternatives. We start with the time value of money, or the notion that money's value changes over time. A simple illustration of this is, would you rather receive $100 today or a year from now? Undoubtedly, the answer is today, and the reason is that it is worth more to you today than in the future. The formulas to move money back and forth in time are shown. Here, PV is present value, or worth at the current time. FV is future value, or worth sometime in the future. The interest rate is represented by I, and N is the number of compounding periods, the time element. Sunk costs cannot be recouped and are irrelevant to the discussion at hand. However, this rule is abandoned in practice more often than not, and may lead to incorrect decisions. For example, tech debt interest of $1,000 is paid in each of the past 2 iterations, yet its removal cost is estimated to only be $1.5K. In the next planning iteration, what should become of the debt? Intuitively, many will argue for its removal, since more money has already been spent in interest than the cost of removal. Although it feels right, this is an invalid argument. Determining the probability that the debt will be encountered again and its likely cost is valid, but the $2,000 already spent is irrelevant. Sensitivity analysis looks to determine which factors impact the decision the most. To perform this type of analysis, one variable is methodically changed over its expected range, while all others are held at their nominal values. If the calculation fluctuates severely with modest changes of the variable, then the problem is said to be sensitive to that variable. Otherwise, it is deemed to be insensitive. Examples of this will be shown shortly. Finally, we need to discuss decision trees and expected monetary value, or EMV. EMV is a risk-based approach to calculating values and is based on probability. The decision tree aspect visualizes the problem and also allows for decision points, as you will see in the following example. To calculate EMV, one must understand the choices, which are shown here as squares, the risks, shown as circles, and the payoffs, shown as triangles. It then becomes a math problem of calculating payoffs in terms of their probability of occurrence. EMV is determined by first working left to right, filling in the cash flows and probabilities to arrive at payoffs. Here, a decision looms, which is depicted as the green square. You may either defer the debt and incur a $7,000 cost, or remove it and incur a $10,000 cost of development. If it is deferred and then re-encountered in the future, an additional $7,000 cost is incurred. That's depicted as the red circle. Here you'll note the probability of reoccurrence is 30% and the probability of non-reoccurrence is 70%. Then, working backwards, probabilistic values are combined at the chance nodes and folded back. Here we have a 30% chance at a $7,000 cost and a 70% chance at a $0 cost, or an expected value of $9,100, which is 0.3 times minus 7,000 plus 0.7 times 0. That value, along with its counterpart, is then rolled back to the decision node, the green square, where the best opportunity is preferred. In this case, the least cost alternative between 9.1 and $10K. Here, accepting the debt is less costly than removing it, thus it is wise to accept it. There have been several studies that look at tech debt from an economic analysis approach, and we now turn to that discussion. The pie graph shown here shows the distribution of research based on a literature review performed by other researchers. The bottom 25% of techniques are excluded from the discussion. For reference, they are the analytical hierarchy process, AHP, total cost of ownership, TCO, return on investment, ROI, marketing approaches, and accounting methods. The remaining 75% are discussed before proceeding to our proposed solution. Most research favors benefit-cost analysis, which is often referred to as cost-benefit analysis. When performed correctly, it is a simple ratio as shown by the formula here. If the result is greater than 1, the project is worthwhile. Note that to compare multiple alternatives, they must be compared marginally, as shown by the second formula. 2 studies are represented here. Zazworka and others evaluated guide classes in terms of impact, the benefit, and effort, the cost, as shown in the plot in the upper right. Here, one would naturally prefer high impact, low effort debt as candidate for removal. The problem with this study is that it does not follow either of the formulas presented above, among other things. Go and others retrospectively applied cost minus benefit analysis to a failed maintenance project, as is shown in the lower graphic. Here, 3 decision points existed, and they proposed that using this technique would have changed the decision at the second point from defer to payoff, thereby saving considerable time and effort. Again, this is not a true benefit cost analysis. Real options refer to decision making under uncertainty, where the decision maker has the option by right and under no obligation to delay decisions in order to allow those uncertainties to resolve either wholly or partially. The choice or opportunity starts with an investment that provides those real options, which fall into one of 3 categories. The option to expand. This allows the manager to build on good fortune, thereby increasing profits as time goes by. The option to abandon or to scale down. This allows the manager to cut the proverbial losses. The option to wait or delay. This allows the manager to buy time before making a decision. Abad and Rue choose a binomial approach in their research. A binomial tree is shown here and is based on the notion that at each point in time the option's value may either go up or go down. The U and D factors are calculated according to the formula shown where sigma is volatility calculated as the standard deviation of the rate of return over time. Abad and Rue argue that this is easily determined from historical data through monitoring, or through monitoring, but we disagree. We also disagree with the up-down nature of the tech debt's value proposition. Although mentioned in literature, the following 2 approaches were not modeled in such a way as to be of use to software managers. A portfolio, in financial terms, refers to a group of diversified investments and is used as a risk mitigation tool. Usually the goal is to maximize profit at a specific risk level. Go and Seaman propose a 5-step process to portfolio management. While the notion of a portfolio of tech debt seems logical, the above approach falls short in that no model has been presented to guide managers as to what to include in the portfolio and what to exclude from it. Essentially, it becomes a list of tech debt. Present value analysis deals with time value of money and pulls all cash flows back to the present time for comparison. It may be calculated using the formula shown. Here, T represents the time of each cash flow, N is the number of cash flows, A sub T is the cash flow at time T, and I is the interest rates. There were no true examples of this approach in the literature reviewed. Tech debt is not a point-in-time problem and should not be analyzed as one. Its recurring and compounding nature is constantly mentioned in research. It is infrequently considered during tech debt management activities. It fits the definition of a decision under risk, and this paper is motivated by the lack of treatment of tech debt management as such. Based on my research, no proposals have been made to address tech debt management using EMV. The goal of this paper, in addition to answering the research questions shown here, is to propose a financially based, simplistic model that managers and engineers may use to process tech debt management. The methodology used was essentially a literature review of the current papers in the ACM, IEEE, and Google Scholar databases. We now turn to the discussion of the proposed approach. Here, we discuss commonly cited effects of tech debt using modified cash flow diagrams. The up arrows represent positive cash flows, or in our case, value-generating software development. The down arrows represent cash outflows. In the first view, tech debt may be considered the reduction of value of output, that is, the difference of the value that could have been achieved if the tech debt were not encountered. Here it is proposed to be either constant or incremental. An alternative view is to subtract the value portion of the above graph and look at tech debt as an increase in cost over time. Again, the cost may be constant or incremental. This cost-based model is the one that is preferred in this paper. In this paper, tech debt is viewed in terms of its cost, not its value. and the principal and interest take on a slightly different meaning than is often found in research. First, principal is considered to be the cost to remove the tech debt. Next, interest is considered to be the cost to live with it. It's important to also keep in mind the three other qualities of tech debt shown here. First, that it is a trade-off, and in keeping with the definition, equal values, or in our case costs, must be traded. Second and third, that like all risks, it has both a time and probability elements which must be considered. Reactive tech debt management is concerned with the decision making in the case that tech debt is unexpectedly encountered during the course of software development. The model here is comprised of 7 steps. First, you must identify the principal, the cost of the removal of the debt. Then you must estimate the cost of living with the debt, and if it's constant or incremental. Third, estimate the probability of future encounters. Fourth, determine appropriate planning horizon. Fifth, estimate the frequency of future encounters within that horizon. 6, model reality as a decision tree. That is, each encounter becomes a new decision point as to whether or not to accumulate the debt or to remove it. Finally, number 7, solve the problem using expected monetary value. An example of this procedure is shown on the next slide. The constraints of the problem are shown in the upper table. Over the next 3 iterations, a 30% chance exists that a particular debt-ridden module will be modified. Removal of the debt will cost $4,000. Accepting it will cost $2,000. The problem is modeled in a decision tree shown, and the results are presented in the table below with probability subject to sensitivity. As may be seen, it is cost-effective to maintain the debt up to 50% probability of occurrence. There are several key points to note before moving on. First, the decision tree has the potential to explode. With only 3 iterations shown, the decision tree is quite large, but can be reduced using reference nodes. Most likely, automation will be necessary to perform analysis on more complex problems. When the tech debt is removed, the probability of reoccurrence goes to 0. In traditional decision trees, subsequent chance nodes, the circles, would not be drawn, but they are here for illustrative purposes. In keeping with the notion of sunk costs, the decision points, the squares, do not take past costs into account. Since this is a constant cost model, the rightmost decisions will always prefer accepting the debt and simply pay the interest on it, since principal is always greater than interest. A very simple sensitivity analysis shown here shows that the decision remains moderately consistent. The same model is solved for 2 additional cases, proving that this model applies to more realistic cases. On the left, the constant cost is replaced with an increase of 10% per encounter, applied to both principal and interest. On the right, we take the incremental cost model and subject it to time value of money by discounting future costs, using an interest rate of 5% per iteration. Note that in both cases, the decision tree structure remains the same since the basic problem remains the same. While reactive tech debt management deals with issues, that is, risks that have become realized, proactive tech debt management deals with true risks, uncertain future events, and may be considered a prioritization problem. In other words, address the most prominent risks in terms of likelihood and impact. However, before proceeding, the context of the problem must be kept in mind. With respect to removal, the problem lies with determining the best candidates for removal. With respect to acceptance, the decision is in the context of a trade-off. That is it worth it to accept the tech debt? And finally, with respect to risk analysis, the decision is how to handle the risk of the tech debt itself in the context of the project. That is, avoid the risk by paying the tech debt up front, or accept it and build a contingency into the plan. With the proactive approach, it is likely that multiple items are under consideration at the same time. One of the benefits of this approach is that it is effectively a present worth analysis since it brings all costs back to the decision point. As such, multiple alternatives may simply be ranked ordered. The steps are: number 1, determine the planning horizon. Number 2, execute the previously discussed reactive model for each tech debt item being considered using that planning horizon. Number 3, discard any tech debt items that indicate deferral as a preferred option. Number 4, rank order those that suggest removal from largest to least cost. And finally, number 5, address removal in the order presented. A few key points to note are: the planning horizon must be consistent across all alternatives. While the approach takes time into account, it does so holistically. Therefore, if a formidable risk is looming, it may be necessary to address it earlier. Sensitivity analysis becomes much more difficult when considering multiple alternatives. A simple approach is to first view sensitivity at the individual tech debt items and then roll it up if deemed necessary. The decision to accept tech debt is logically the inverse of its removal. Accept the tech debt when it's financially responsible to do so. The steps in doing so are: number 1, determine the overall planning horizon. Execute the reactive model for each tech debt item under consideration using that planning horizon. Do not accept any tech debt items that indicate removal as the preferred option. Rather, incorporate them into a removal plan. Number 4, numerically order those that suggest deferral from largest to least cost. And number 5, monitor the acceptance list periodically of the changes. With respect to risk management, the procedures just discussed are excellent techniques. They're capable of realistically identifying risk reserves, which is money that we'd set aside for addressing risks if they occur, in the case that the system actually contains debt. In the case that the tech debt is being considered for acceptance, the acceptance procedure helps quantify the newly added risk item. It helps the risk manager form a plan to address that risk. Perhaps one of the biggest benefits of treating tech debt as a risk is that it will force review upon the tech debt items along with the other risks of the project. Those that find themselves able to quantify tech debt are likely best served by treating it as a risk acceptance problem. Acknowledge its existence, quantify it as described in this paper, plan for it, and remove it only when and if it occurs. Here, I discuss the threats to validity and future work. First, I assume that principal and interest may be accurately and easily estimated. This may not be the case, and if the cost of doing so is prohibited, this model cannot be used effectively. It excludes other factors from the equation, such as employee morale. And finally, it may prove difficult to scale. With respect to future work, empirical studies and experiments are needed to prove this to be a truly viable solution. As mentioned, human factors should be considered for the cost profile, and survey information should be considered as an alternative to sensitivity analysis. Survey information helps answer questions such as: how accurate do we estimate the probability of occurrence? In conclusion, I showed 4 other economic-based methods of tech debt management. The benefit-cost approach, while simple, does not address tech debt's recurring nature and is often implemented incorrectly. It is also difficult to compare multiple alternatives and thus prioritize them using benefit-to-cost ratios. Real option analysis proved to be a difficult model and does not handle reoccurrence either. The up-down nature of the value proposition is also questionable. The portfolio approach is essentially a list of tech debt items. Research lacks common sense approach to managing this list. Finally, present value is useful in tech debt management, but as a means, not an end. The model that I present overcomes the shortcomings of the models just discussed. It is based on proven economic analysis techniques such as risk management, sensitivity analysis, and decision theory. Furthermore, it provides a mechanism for properly prioritizing risk. Since it mimics reality, it's a simple model to understand. I believe that this is a viable mechanism for managing technical debt. That concludes my presentation. Thank you.